Okay, all right, catalytic hydrogenation. So just like in alkene, so add hydrogen in the presence of a catalyst, nickel, palladium, platinum, pick the one you want, add two hydrogen atoms on these two carbon, you get an alkane, right? In alkyne, of course, you're gonna get, so it's in addition, exactly the same. You go to cis alkene first, but you can't isolate it because the next equivalent we go in right away. All right, so you go to alkane. So basically, alkyne, you go all the way to alkane. You add two molecules of hydrogen. This is just one molecule. All right. Now, this will happen if you remember the energy diagram. So without the catalyst, the activation energy of this process is way too high. It's not going to happen. Adding just hydrogen without a catalyst, not going to go on to the alkene right away. Same thing with the alkyne. Okay, it won't do it. But adding the catalyst, it reduces the activation energy of the first process, the first addition and the second addition. So the reaction go much faster to all the way to alkane. Right? Now the question is going to be, what if we want to synthesize an alkene from an alkyne? We want to obtain an alkene. What do we do? Well, one thing we can do, we can design a catalyst that catalyze only the first addition and not catalyze the second addition. Okay, there's a mechanism into it, but the logic behind it right here. So the reaction is not gonna happen if the activation energy is too high, but the catalyst make activation energy from both addition low, so both addition occurs. What if we want just the first addition, but we don't want the second one? Well, we decide a catalyst that have the high activation energy on the second addition, but keep the first addition low in activation energy. Look right like this. All right. So we call this catalyst Lindlar's catalyst. So we poison it, or partially deactivate. They call it poison. Okay. So we poison this catalyst with the palladium using barium sulfate, quinoline, methanol as a solvent. Right. You don't have to memorize all this. Right. Just write down hydrogen gas and then Lindlar catalyst. We got it. All right. So what does this guy do? This partially deactivated palladium. So we put all this to palladium. So partially deactivated. This palladium can catalyze the first addition, but not the second addition. Keep the activation energy of the second addition high, so it won't do the second addition there. All right. So basically, you stop with a cis alkene. All right. And partially deactivated. Right, so catalyze only the first addition. Right, and another, you can write it just right here, so you don't have to memorize the whole thing. Just write down hydrogen gas and then Lindlar's catalyst. We know what Lindlar's is, the person's name. Okay. Another way you can do this, we use hydrogen gas and use nickel boron complex Ni2b. That's the same thing with Lindlar's catalyst. All right, either one works for you. Pick the one that you like. Okay. All right. So Lindlar's catalyst will give you a cis isomer, cis alkene. All right. Some example. This is like the real life example. This is going to be. One is in a pharmaceutical company called Hoffman and La Roche. I don't know how to say it. Right. Anyway, so this company synthesized vitamin A, right, from this alkyne analog. Use Lindlar's catalyst, add hydrogen onto this alkyne to form a cis isomers of the product, right? And this is what vitamin A. So, and they do this in a large, like a big scale, large scale, and you sell it. Okay. All right. So catalytic hydrogenation. If you do it exactly like the way you did with the alkene, so add hydrogen gas and add one of these catalysts, you go all the way to alkene. But you can stop at alkene, cis alkene particularly, use a Lindlar's catalyst or nickel boron complex. Right? Don't forget to add hydrogen. You need a hydrogen gas there too. Right? And if you want a trans isomer, we use right here metal sodium. So this is a solid. This is metal sodium in liquid ammonia. Right? So you add sodium in liquid ammonia, it will convert an alkyne to a trans isomer, trans alkene. Here's how it happened. Let's take a look right here real quick. When you add sodium into liquid ammonia, and just remember liquid ammonia, you have seen one time with the sodium amide, the acid-base reaction. Liquid ammonia is really cold because we have to keep in ammonia is a gas at room temperature. The boiling point is negative 33 degrees. If you want to make it stay as a liquid form, you have to lower the temperature by a lot. Right? Lower than negative 33 degrees. Anyway, adding sodium into liquid ammonia the nucleus of sodium and electron of sodium get pulled away from one another by ammonia, right? So basically, electrons get pulled away from sodium, and sodium becomes sodium ion, and right away the solution turned blue. Looks something like that, right? Adding sodium. So this is, let's say this is liquid ammonia. Add like a sodium metal into it. The reaction reaction flags turn blue right away. The solution turned blue, and those are just a bunch of electrons floating around, millions of particle of electrons floating around, ready to do reaction. All right, and then you're going to add an alkyne into it, and this is what's going to happen. Let's take a look at the mechanism. So, sodium, we're going to use sodium's going to use a single electron, right? Just the single electron add on to the alkyne. Looks something like that, right? So note that I use a fish hook arrow to show this single electron transfer, not the double hook double hook arrow. That's for 2 electron transfer. This is single electron transfer. Okay. All right. So 1 electron from sodium, 1 electron from the pi bond. All right. So 1 electron from become the lone pair, become a lone pair. Right. The other electron of this pi bond become just a radical right there. So we have what's it called, a radical anion, right? Which is really unstable. Now ammonia, which is a solvent, this anion will go grab the proton transfer. You get the first proton there, first hydrogen gets in there. All right, and the second for the second radical, the radical is not going to do reaction right away. We'll get another electron from sodium. So we have a sodium floating around. This electron is going to pair up, become a lone pair, and then get another proton from the solvent ammonia. Here we go. You get a trans alkene there. All right. Now, what makes this reaction go trans? Can you go cis though? Something control the stereochemistry trans. This guy right here. You can go cis and trans, right? Either way, you can go cis and trans, but cis is not as stable as trans because of there's an electron repulsion there. So the trans is more stable. So trans is going to go forward and do a reaction, go much faster than the cis proceed. Okay. All right, and the yield is pretty good, 80%, about 80%. So get this guy as sodium and liquid ammonia, you got about 80% trans, 5 decyl to trans, 5 decene, about 50%, about 78% yield. You get trans right there. All right, okay, let's test real quick. So let's say you get what's going on. So we have this compound alkyne right there. Oh, go to the right. So hydrogen and a bunch of things in there. Can you guess what this is? That's a Lindlar's catalyst. Yeah, there are multiple recipes of Lindlar catalyst. This is one of them. If you see palladium and a lot of things going on there, quinoline, that's tell you that's a Lindlar catalyst. So we partially deactivate palladium, make this alkyne, make a palladium less active, so they can add hydrogen gas only one time, not twice. You get a cis alkene. Go on the other side. So sodium in liquid ammonia, you get trans. All right. All right, come down here. So this you have to add the reagent. So go to the right, you get cis. So decyl alkyne, go to cis alkene, totally Lindlar's catalyst. Right. So hydrogen and Lindlar's catalyst. On the left side, you get trans. So sodium in liquid ammonia. Okay. All right. Let's moving on to the next reaction.